Hello and welcome to 6. I'm Norman Wahlberger and this is an elementary course in pure mathematics. Today we're going to be looking at cycles and the 3-4 bridge. So although we're primarily interested in 6 things, it will be important for us to also look at smaller collections like 2, 3, 4, 5 also. Today we're going to be concentrating on 3 and 4. And there's a remarkable connection between the combinatorics of 3 and the combinatorics of 4. This remarkable connection, which we call the 3-4 bridge, actually has applications to a lot of classical mathematics, including geometry of conics going back to ancient Greek times, as well as to the important problem of solution of polynomial equations, in particular solutions of quartic equations. And I will explain these connections in a later video. Also today we're going to be looking at cycles, which are additional kinds of combinatorial objects that we can create from a finite collection. So just a very quick review of some concepts which we've already introduced. Primarily the ideas of the nodes, which are the numbers from 1 to 6. The concept of an edge, which is a 2 set of nodes like this thing here, set consisting of the nodes 2 and 5, and here is our abbreviation for that edge, 2, 5. And then a meet is a 2 set of disjoint edges. So there's an edge here, there's an edge here, and these edges are disjoint in the sense that they don't share any nodes. And an alternate notation for that is 1,4.35, where we arrange things so that the things are in increasing order and the lowest term is to the left. A triangle is then a 3 set of nodes with that kind of notation, and then a pair is a 2 set of non-intersecting triangles. So for example, 1, 4, 5 and 2, 3, 6, that is a pair. There's a triangle, they don't have any nodes in common. And then here is our preferred notation, short form for that pair. Today we're going to introduce a new concept called a cycle. And because it's an important concept, we're going to capitalize it. So we're relying very much on this capitalization idea. It's really a German kind of notation, very useful so that it flags the fundamental notions that we're introducing. So to separate our usage of these terms from perhaps common usage in everyday English. So what is a cycle? So a cycle is a set of edges, things of this kind, where each node that appears does so exactly twice. For example, here is a set of edges. It has 4 edges. The edges are 4, 5, 1, 2, 2, 4, 1, 5. And it's a set, so these things are unordered. We could swap things around and it would still be the same set of edges. Now these edges have a certain interesting property. The node 4, for example, appears in this edge, and it appears in this edge, but no other edges. So it appears exactly twice. The node 1 appears exactly twice. The node 2 appears exactly twice. The node 5 appears exactly twice. And the nodes 3 and 6 don't appear. So the nodes that do appear exactly twice. That's what makes this set of edges a cycle. Actually, we'll continue the usage where we sometimes append a number in front of a data structure. So this would actually be more specifically a 4 cycle to denote the fact that it has 4 objects in it. Now we're going to represent this kind of object in a very specific way in this geometrical configuration where we have 6 points on the plane. They are labeling our basic nodes. And then to each one of these edges that appears in this cycle, we're going to just connect, form a line segment between the corresponding nodes. So the line segment there between 4 and 5, the line segment there between 1 and 2, the line segment here between 2 and 4, and the line segment here between 1 and 5. Once we've done that, we see why this is reasonably called a cycle, because this collection of edges really has a kind of continuous property. You can actually walk around it all the way and come back to where you started. So for example, if you start at some random spot, say 2, and you head in one of the two directions, let's say you go 2 to 1, then once you get to 1, you've used one of the edges coming in, so there's exactly one more edge going out. That will then send you in this direction. And then once you get to 5, there's another edge emanating from that, going to 4, and then there's another edge emanating from 4, going back to 2, and you're back to where you started. So it's like a path in the woods that you can traverse in either direction. Okay, it doesn't have an orientation. We're not prescribing that we have to go this way or this way. You can go either direction, but it has the property that you visit whichever nodes that you do visit exactly once. You don't come to a node and then later on come to the node and then come back again. Once you get back to the node that you started with, you've gone through the entire path. So it's a cycle. So a cycle determines a closed path which visits a node at most once. And now we want to introduce some more compact notation for a cycle. So instead of considering this rather cumbersome notation, the cycle consisting of the edges 4, 5, 1, 2, 2, 4, 1, 5, we're going to represent it in this compact form with a 1, a 2, a 4, a 5, and then the whole thing enclosed in angular brackets. So we're introducing this new notation so that when you see something like this, you say, aha, these angular brackets, it's alerting us to the fact that we have a cycle here. So where does this thing come from? So what we do is we start on the left with the lowest node because our 6 nodes are ordered, so there's the smallest one. Okay, so 1 appears in this case, so that's going to be the smallest one. So we start with 1. That's corresponding to starting our path through the woods at the smallest node, which is 1. Now, we've seen that there are 2 directions to go in. Here, we could go to 2 or to 5. We're going to choose the direction towards the next smallest node. All right, so we're looking in the direction 2, we're looking in the direction 5. 2 is less than 5 in our ordering, so we're going to head off in the direction 2. So we start with 1 and then we go to 2. And then after that, everything is determined because once you've reached a node, there's only one way of exiting it. So after we've gotten from 1 to 2, then we have to go to 4, and then we have to go to 5, and then we go from 5 back to 1. So you should think about this as representing this loop, this cycle that goes all the way to the end and then back to 1 again. So this has the very important advantage that this notation that we've introduced is unique. Okay, so there are not going to be 2 different ways of representing the same fundamental object. That's very useful when we want to compare our results with somebody else. So we can quickly see whether these 2 cycles are the same or not. Okay, now let's look at some interesting smaller cases. How about a triangle? If we have a triangle which is a 3 set of nodes, for example, 2, 6, and 5, we claim that determines a unique 3 cycle. A 3 cycle is a cycle with 3 elements. Here it is. We connect 2 and 5, we connect 5 and 6, we connect 6 and 2. In fact, we connect all 3 nodes. So there are 3 edges. So here's the triangle whose short form is 2, 5, 6. And now we're associating to that the cycle whose edges are the 3 possible edges that you can form from these 3 nodes. 5, 6, 2, 5, and 2, 6. And now using our compact angular bracket notation for a cycle, this will be represented by the cycle 2, because that's the smallest node, followed by 5, because that's the smallest node that you can get to from 2, followed by 6. So this is the name of this cycle, and there's only this one cycle that you can form from these 3 nodes. Just a quick word, what happens if you just start with 2 nodes? Can you build a cycle from 2 nodes? Well, that would be like the edge 1, 2, followed by the edge 2, 1. But if you try to make a set out of that, the edge 1, 2 the edge 2, 1. Well, 2, 1 is the same as 1, 2. So that would be a set with two elements which are the same. And a set does not allow repetition. So that's not a valid set. So in fact, there are no cycles that you can create from 2 points. You need at least 3 points to be able to create a cycle. So this is the simplest kind of cycle that we can get. Now, to go a little bit further, we want to introduce bigger analogs of triangles and actually of edges. So an edge was a 2 set of nodes. A triangle was a 3 set of nodes. So it makes sense for us to sort of continue the pattern and give some names to 4 sets of nodes and 5 sets of nodes. Well, a 4 set of nodes will be called a quadrangle, like triangle, quadrangle. And there's 15 of them. And here is what a quadrangle looks like. It's a set of nodes, and there's 4 nodes in the set. In this case, 2, 5, 1, 4. And here is, not surprisingly, the short form representation of that, where we just list the 4 nodes in order of size. 1, 2, 4, 5. Now, this particular quadrangle uses 4 out of our 6 nodes. So there are actually 2 nodes that haven't been used. In this case, 3 and 6. And those 2 nodes form themselves an edge, the edge 3, 6. So this quadrangle is, we could say, opposite the edge 3, 6. If we know the quadrangle, then we know the edge. And conversely, if we know the edge, then that uniquely determines the remaining 4 nodes, which is the quadrangle. That means that there is a mapping or a bijection, we say in mathematics, a correspondence between quadrangles and edges. For every edge, there's a quadrangle. For every quadrangle, there's an edge. That's an easy way of seeing that there are going to be 15 quadrangles because we know there are 15 edges. Of course, we can also list them, and you might like to do that just to check that actually that argument is correct. Okay, having 4 sets of nodes, what about 5 sets of nodes? Very natural. So let's call that a pentagon. So a pentagon for us, and also capital letters, telling us that this is a special object in our little theory. It doesn't necessarily directly connect with the usual usage of the word pentagon in other parts of mathematics or maybe in ordinary life. So for us, a pentagon is a 5 set of nodes. For example, here's a 5 set of nodes. 6, 1, 3, 5, 4. And the canonical way of writing that can be consistent. That's the same as the pentagon 1, 3, 4, 5, 6. We just list the nodes in increasing order. Now, in this case, there's obviously one node that's not contained in the pentagon, namely the node 2. So we could say that this pentagon is opposite the node 2. And that makes it clear why there are going to be 6 pentagons, because there are 6 nodes, and for each one of the nodes, there's an opposite pentagon. Great, so now we come to the 3-4 bridge, this mathematical connection between 3 things and 4 things. So it's all because of this statement that any quadrangle determines 3 4 cycles. So we saw that if we have a triangle, it determines a single cycle. But if we have a quadrangle, 4 points or 4 nodes, then there are 3 associated cycles of length 4. And 3 corresponding meets. Okay, so let me explain this. So let's start with a quadrangle. Here's the quadrangle 1, 2, 3, 5. That's just a set of 4 nodes. 1, 2, 3, 5. Now associated to this set, there are 3 4 cycles. And here they are. Okay, so the first one here in this list is the cycle 1, 2, 3, 5. We go around in this order. There's the name. Here's the second one. 1, 3, 2, 5. And here's the other one. 1, 2, 5, 3. Now here on the bottom are the 3 corresponding meets that we can create from these 4 points, or 4 nodes. Namely, we can take the meet of the edge 1, 3 and 2, 5. The 1, 3 is representing this edge, and 2, 5 is representing this edge. Notice that these are the 2 edges which are not appearing in this cycle. So if you have 4 points, then altogether there are 6 possible edges that you can form from those 4 nodes. Right? There are these 4, but there's also the edge 1, 3 and the edge 2, 5. So this meet down here is just the set consisting of the 2 edges which are not appearing in the cycle. Over here, the edges which are not appearing in this cycle are the edges 1, 2 and 3, 5. And there's a picture of them. There's the name of the meet, the set of edges consisting of the edge 1, 2 and 3, 5. And over here, the edges which are not visible are 1, 5, right there, and 2, 3. That's the meet 1, 5, 2, 3. So there's a correspondence between these meets, which we've already seen before, and these 4 cycles that are determined by this particular quadrangle. Now, when we were talking about meets before, we saw that we could visualize those meets also very efficiently by just looking at the intersection or the meet of the 2 corresponding edges. So another way of thinking about what this meet represents is it's representing that point there. Okay? And the point that's represented by these 2, well, would be the point just a little bit down here where these 2 lines would meet if we extended them. Similarly over here, the corresponding meet would be the point over there that is obtained by meeting those 2 lines. But we don't actually have to have those physical points in evidence. We can also think about the meets as just being the pair of lines, pair of essentially disjoint lines. And then it's clear that each one of these pair of disjoint lines matches up with one of these 3, 4 cycles. So here's the 3-4 bridge, okay? We start with 4 objects. And then by considering these cycles, or if you prefer, by considering these corresponding meets, this quadrangle of 4 points determines 3 cycles, or correspondingly 3 meets. So from 4 points, we get 3 cycles. That's the bridge between 3 and 4. Now I want to stress to you that even though we have these geometrical ways of picturing what we're doing, ultimately the theory that we're talking about is entirely combinatorial. It doesn't really depend on pictures, even though as human beings we like to have pictures because it's easy for us to process visual information. But the actual combinatorial objects might have different physical or visual manifestations. And I want to show you another one. So another way of thinking about interpreting this theory of 6 that we're building up. So that involves a 3-dimensional representation. We kind of go up in complexity a little bit and consider 3-dimensional things. So let's consider a quadrangle, which is 4 nodes, as a tetrahedron in 3-dimensional space. So for example, here is a tetrahedron. Okay? This is actually a regular tetrahedron made out of equilateral triangles. It has 1, 2, 3, 4 vertices, and it has 4 faces, and it has 1, 2, 3, 4, 5, 6 edges. So this is another way of sort of thinking about what a quadrangle is. And here's sort of a picture of it, a planar representation of this. So you should think of the 1, 2, 3 faces sort of facing you, and this this 4th one is sort of maybe behind or partially behind, something like this. So there's this edge back here that maybe you can't see so well, something like this. Okay, so that's representing the dotted line. That's behind this space here. Okay, so that's another way of visualizing a quadrangle. If we do that, then a cycle, or a 4 cycle, say the 4 cycle 1, 3, 2, 4, can be represented by a path on the edges of this tetrahedron. In this case, the path that starts at 1 goes up to 3, and then over to 2, then over to 4, and then back to 1. So the little grated edges, that's a path on the tetrahedron. That's another way of thinking visually about what a 4 cycle is. In some sense, that's like a quadrilateral in three-dimensional space, which is not planar. It's what's sometimes called a skew quadrilateral, so a non-planar quadrilateral. And corresponding to this, there's of course a meet, and the meet is what you get when you consider the two edges which are not contained in the cycle. In this case, 1, 2, and 3, 4. So in the tetrahedral story, that would be a pair of edges, in that, say maybe this edge right here, together with the sort of opposite edge on this side, which doesn't meet this edge. We have these two different directions, two different lines in space, which are not meeting. Sometimes we call them skew lines. That's an interpretation of the meet of these two edges. Notice that in that interpretation, there is no common point of these two lines, so it doesn't make sense to visualize the meet as a point. It's better to visualize the meet as this pair of lines. So thinking about a pair of lines or thinking about the corresponding cycle, it's more or less equivalent. Okay, so for your homework, I want you to think about how many 4 cycles there are and how many 5 cycles there are, and maybe even how many 6 cycles there are. So 4 cycles is easy because we've seen that every quadrangle is associated to 3 4 cycles. And how many quadrangles are there? Well, we said there were 15 because there's basically one for every edge. So there should be 15 times 3, which is 45 different 4 cycles if you're considering all 6 nodes. And for your homework, I want you to figure out how many 5 cycles are there and how many 6 cycles are there. So in today's lecture, we've introduced this important idea of a cycle, and we've also had a look at the connection between 3 and 4. That has a lot of other applications, and it's also a step towards another kind of bridge, which is going to be even more important for us in this course. I'm Noah Wildberger. Thanks for listening.